All right, thanks. So as you can tell from the slide, my name is Ted Neward. I'm currently the Director of Technology Culture at Quicken Loans, also known as Rocket Mortgage in some circles. And in this particular conversation, what I'm going to do is I'm going to talk to you a little bit about polytechnical careering. Now, to be blunt, most people's reactions when they hear this particular title or this particular phrase, what are you talking about? That sounds like you just threw together a bunch of syllables and, what does that actually mean? Well, for quite a while, we've been hearing people talk about the idea of being polyglot, which is, of course, Latin for multiple languages. And by the way, quick trivia question. Does anybody know what you call somebody who only speaks one language? Yes, that's correct. You call them an American. The other thing, though, within the technology space, it's not just about knowing multiple languages. It turns out that we actually derive benefit from knowing a variety of other kinds of tools and technologies beyond just the languages that you use, C Sharp, Java, F Sharp, etc. And so I actually did a little bit of, let's just call it research, but truthfully, I did some Googling. And I found that there are two other phrases that kind of capture this notion. Polypreclusio, which is the notion of having multiple storages, that is to say multiple databases. And polycrepido, which is the notion of multiple platforms or foundations. And the idea here, very bluntly, this is why I generally prefer the term polytechnical, is that you are bigger, you are wider, you are broader than just the particular dev stack that you may use on a day-to-day basis. If you spend a lot of time in the .NET space, you've also learned things around Java and JVM and so forth. You've also learned some things about JavaScript, such as Node.js. Maybe you've even played around with some Electron or Elixir and so on and so forth. So you've got a broad foundation. Because when you're polytechnical, you actually understand that there is value in these different technologies. Yes, on the surface, the CLR and the JVM are kind of like evil twin brothers, almost like evil princes seeking to, decide who will, take control of the kingdom when the king dies. The king, of course, is COBOL. You don't believe that there's just one answer. You don't believe there's just one anything. There's not one way to store it. There's not one way to express your ideas and concepts. It's not just one way to approach how we build things. And in many respects, you embrace this idea of taking from each language as it provides and applying to each project as it needs. And yes, I am definitely paraphrasing good old Marx and his Marxist manifesto and so forth. Now, having said all of that, to a lot of people, this sounds like a ton of work, and this sounds like there's not a whole lot of payoff to doing this. In many respects, it sounds like one of those things that, we tell people they should do, but we don't always actually believe that people will do it. I mean, as a matter of fact, Dave Thomas of the Pragmatic Programmers has said that you should learn a new programming language every year. And frankly, a lot of people, when they hear that particular message, they kind of roll their eyes and go, yeah, sure, who has the time? And more importantly, what exactly does that do for me? Why exactly would I bother to do this? Because for many folks, when you look at the C# language, it's basically Java, or when you look at Java, it's basically C#. There's some language differences there. I mean, there's a couple of things. C# has explicit syntax for properties. Java does not. Java's now introduced a records type that C# may roll into a future version, but for the most part, they're all the same. Why exactly does that really do anything for me? And that's a very fair question. It really is, because in many respects, you could really chase this. You could chase this rabbit purely for its own benefit. As a matter of fact, if you look behind me, there's a shelf back there that's filled with a ton of books. There's a shelf over there and there's a shelf down there. And, that really starts to become overwhelming. Are you saying I have to learn all of these things just to get some of the benefits? No, Now, I mean, I'd love to, because, you know, those book authors would love to get their book royalties. But truthfully, it's about the concepts that you get exposed to that then lead you to make realizations in other places. And let me walk you through what I mean by that. For those of you who have never learned the programming language Haskell, we're about to. This is a Haskell list. Now, under the hood, basically, it's a linked list. Actually, it's an immutable linked list, but that's an implementation detail that we really don't need to worry about too much right now. The point is, this is a list. As you can see, we use the let syntax, which, again, Haskell being a functional language, really wants to embrace some of that mathematical notion of syntax. So where other languages might say var, we use let. And fundamentally, what we're doing is we're creating a binding. We're saying this name numbers is now bound to this list of 3 numbers. So far, so good? Excellent. Let's move on. Here, we're going to exercise a couple of top-level functions that do various things to these lists. First of all, you can notice the curly brace dash. That's your comment syntax. That's basically to say this is where we put comments. And I'm using that just to show you what we'll actually display when we call the print function. The first function you see is head, and what that does is that peels off the first element of the list, as you might well imagine. And the last function does pretty much the exact opposite, peel off the last element of the list. Now, both of those peel off an individual element of the respective list, which is different from the tail function, which says return to me all of the elements of the list in a list except for the first one. So you can imagine for a second that if I wanted to iterate through this list, I would use head to peel off the first element, do something with it, and then take tail and recursively do what I just described. Because when tail is called on a list with only one element in it, it returns an empty list. There's no more elements in the list, and we can bail out of our recursive function. Functional languages really like recursion, by the way, for these kinds of reasons. There's also a function called take, which says specifically, I want to reach out and take the X number of elements from the list as a list. So here, when I take 2 off of the numbers, I'll get a smaller list, but I'll get a list of the elements 1 and 2 present. Everybody still with me? Haskell's not that hard, right? Let's keep going. Now, one of the things that Haskell also supports, which is actually fairly common in a number of languages, is this idea of a range. So notice here when we use the square brackets and we use 2 dots, not 3 dots, but 2 dots, that indicates that we are creating a range of elements. And in this particular case, it's a range of numbers from 1 to 100 inclusive. So that when we print this number range, we will get 1, 2, 3, all the way up through 100. Pretty straightforward. But ranges also allow us to do some things with the lists, or with the range. So here, for example, when I say 2, 4, 6, 8, that is an indication to Haskell that this range is actually supposed to skip by 2. And it does that by inferring the difference between 2 and 4. And there's a variety of different ways we can do this, but fundamentally, it's still the same basic idea. Give me a list of numbers that ranges from, in this case, 2 all the way up through 100, skipping by 2. Yeah, that's okay. I mean, that's not terrible. But it's, again, nothing too difficult. Some of this functional language stuff is actually pretty straightforward and easy when you start to think about it. At least that's where I was in my head as I was going through Haskell. And then I got to comprehensions. Now, a comprehension, in many respects, you can think of it kind of like the body of a for loop. I'm sure there are some functional programmers out in the world right now who are cringing and throwing something at the screen. Remember, that's your laptop. If you destroy your laptop, that's on you, all right? Let's just be really clear. In this first example, what I'm doing with other evens is I'm actually saying that I want to apply the range 1 through 10. That's what the left-hand arrow here is doing, is I'm applying each element of that to the value X, And then what I want the results of this comprehension to do is to produce a list where each value in that list is just X. So literally what we're doing with other evens here is we're going through this list, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each time that value will be applied to X, and then we're just returning X. So other evens is actually kind of a deceitful name because it really has nothing to do with even numbers at all. It's just giving me a list of 1 through 10. Okay? So fundamentally, this is used, if you're familiar with other languages, JavaScript, F#, etc., this is actually producing just a list. This is a transform or a map, as it's sometimes called in some languages like JavaScript or whatnot. You can see the same comprehension at work here inside of the squares comprehension. The squares list will now have 1, 4, 9, 16, 25, math is hard, 36. You get it, right? And so essentially, this comprehension is a way of saying we apply these results on the left-hand side to the items that are identified via this iteration, if you will, on the right-hand side. Now, FizzBuzz, of course, is one of the great challenges that face every person who's ever wanted to interview at any programming company. It's not really, but it's a way that companies have evolved to be able to determine whether or not you are capable of writing code. Now, granted, I am a director, which means I am a manager, which means that any ability to write code has long since fled my body. But fortunately, I wrote this bit before I became a director. So let's see if I can remember how this works. First of all, we can see at the bottom of this, we see X. We're applying the range 1 through 25 to X. Okay, so each time through the body of this comprehension, X will contain whatever the current working value is. All right, so far so good. Now, in Haskell, because Haskell is a functional languages really like the idea of expressions instead of statements. See, in C# and Java, the if is it's a statement. And the difference between expressions and statements is that expressions return values, whereas statements do not. So in this particular case, Haskell's if expression returns the result. So for example, if we say x mod 15, which is the modulo operator, it's backticked like that because I want to use it as an operator as opposed to calling the mod function. This is one of those things that Haskell allows you to do. So x mod 15 means anything divisible by 15, which if we remember FizzBuzz says anything divisible by 3, we should return buzz, and anything divisible by 5, we should return fizz, and anything that's divisible by both, we should return both of those. Or maybe it's the other way around. Yeesh. I may have just not gotten a job at any of your companies, but remember, I'm a manager, so don't ship any of this code. But the point here is that if it's divisible by both, it means it has to be divisible by 15, and the modulo operator means that it would return 0, in which case I print out both. So in this scenario, what I'm doing is I'm basically saying if it's divisible by 15, return BuzzFizz, else, and now we do the next part of this. And if you're thinking in your head that the if else or if then else in Haskell sounds a lot like the question mark colon operator from Java and C#, you get it. The question mark colon operator is an expression, whereas the if statement is a statement. And Haskell just says, let's just make the whole thing an expression. So back to the code. If x mod 15 is 0, then we yield back BuzzFizz. If it's mod 3, we yield back buzz. If it's mod 5, we yield back fizz. Else we show, which is to say, just convert that integer into a string, because the result of each of these branches has to be a string. And yeah, what we should get as a result from this is we should get a list of strings, which will be basically 1, 2, buzz, 4, fizz, yeah, you get it. Wow. Okay, so this comprehension stuff is actually, there's some interesting power to it, because technically all of this is one expression. So we just answered the whole FizzBuzz with one expression, obviously made up of smaller expressions, but in of itself, that's interesting. But I don't know exactly how powerful or how useful that really is. Let's keep going. Now, one of the things that Haskell supports is this notion of an infinite list. And I got to tell you, folks, the first time I ran across this, I was absolutely confused out of my head. Because here, this forever is literally a list that will stretch forever. As a matter of fact, just for fun, I said, I want to print forever. And sure enough, my screen filled with just numbers. And after it got to about 8 or 9 digits in size, because I accidentally left it running overnight, I said, okay, I believe you. It is forever. This list goes on forever. Which then raises a really interesting question, because if this is a list, the way that we think about lists in Java or C#, having a list that goes forever is kind of a contradiction. I mean, because technically, if this is a list, if this is a collection, then trying to store this collection in memory, I mean, by definition, if it's infinite, no computer on the planet has enough RAM to be able to store an infinite list. I mean, no computer ever that could be built could ever store an infinite list. And there are some interesting things we can do with this. There's also the cycle function, which says that we want to create a list that essentially continues to cycle, as you might imagine, over the list that is given it. So here, cycle basically says, I will create an infinite list out of the list that contains one element, love. So we have now created a list filled with love, which, it's a great idea, but we're still back with the idea of how do we work with an infinite list? I mean, I can take 3 elements from that infinite list so that I get love, 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 and now this is basically the closest I will ever get to being a beetle. But fundamentally, this notion of infinite lists, man, it absolutely just blew me. I mean, I was just like, this is nuts. How do I store? How do I hold? How do I contain a list that stretches on forever? I mean, what kind of list ever goes on forever? And by the way, just as a terminology note and a tiny bit of foreshadowing, Haskell refers to these lists as streams. The Java community actually picked up on this terminology, partly because they were a little bit later to the game than the C# folks. But this notion of an infinite list, a list that goes on forever, is frequently referred to in Haskell as a stream, to differentiate it against a finite list, to be quite precise about the terminology. But I'm still this notion of a list that stretches forever. I mean, how do I iterate over a list that goes forever? I mean, because you have to have the collection finished. You have to have the collection done in order for this to work. And that's when somewhere through the very thick cranial tissue right here, things started banging on the back of my head, and it became more apparent to me, maybe this is actually driving towards the idea that an iterator isn't always attached to a collection. That in fact, as you start to dig into the notion of how Haskell implements these infinite streams, what they actually do with these comprehensions, and I'm going to break protocol here for a second. I'm going to go back for a bit. Looking at this comprehension, when we start talking about ranges here, what we're really talking about, 1.10, that's not actually a list. That's not actually been realized in memory. We don't actually have a collection of 10 numbers. I mean, at the end of the day, the compiler could do it that way if it thought that that was the better way of approaching things. But usually, when you see something like this, when you talk about a range object, What you're actually getting back is something that knows how to manufacture the next element in the list. So if we go back to our very simple example, even here, in our first range, 1 to 100, we didn't actually get 100 integers in a nice linked list. What we actually got was a function that came to us. And again, this is one of the great powers of Haskell as a functional language. We didn't actually know what we got back. We just knew it was bound to number range. And then every time somebody wanted to use an element from number range, every time we wanted to take an element from number range, the function that was hiding below the surface there said, all right, I currently printed the value 1, so now I'll give back 2. You asked for 2, and now I'll give back 3. Once we're done with 3, I'll give you 4 and 5 and 6 and all the way up through 100, at which point I say, and there's nothing left. The list is complete. This is why it's so easy for that evens range to also work so well, because now basically we're just stepping through by 2 instead of by 1. So in each case here, what we're getting back from this range is a function. And then when we look at these here, now it becomes a little bit easier to see that essentially we're calling a function to get the value for x, which then gets applied to a function. And you start to see the power of how Haskell wants to be able to compose these functions, which then means that these infinite lists are essentially just functions, or if we want to use the object terminology, they're objects. And these objects know how to produce the next value in the stream or in the list. You know, it's interesting because, excuse me, when we start thinking about how both Java and C#, when we start thinking about how they do iteration, we actually have objects that can be used here. As a matter of fact, many of you will be familiar, especially if you're old like me and you got gray somewhere in your hair. You'll remember the iterator design pattern that was released as a part of the Gang of Four patterns back in, let's see, how long ago was that? My Gang of Four book is over there on that shelf. I think it was like 1995, if I'm not mistaken. It's been a while. But the iterator pattern suggests that we create an object that knows specifically how to iterate through the collection. But you know, what if the iterator itself knew how to create that next element? Instead of actually reaching to the collection, instead of putting all the intelligence in the collection and the iterator just basically gives you the next one, what if we put more intelligence into the iterator so that we could create an iterator that didn't have to operate over a collection? So, for example, if I'm going to use C# because at Quicken Loans we're a .NET shop, .NET and JavaScript and HTML and CSS and all those other things, but we use a lot of C# inside. So in C# we have two interfaces that represent this concept. We have the enumerable, which says this is how I get one of those iterators, which in C# we refer to as an enumerator. And in this particular case, if the collection represents both, or I'm sorry, if the iterator doesn't have a collection, because usually the collection is what's enumerable, so then we actually want this comprehension to know that it is both collection, and I'm actually going to stop with that word because that's not really the right one to use. It is both stream and iterator both. So here, what we see is I'm using some of the newfangled C# syntax to make sure it all fits on a slide. So when we get a hold of the enumerator, we're basically returning the same object. So that's just returning this. The enumerator wants to know what the current element is. So if this is going to be a collection, I'm sorry, if this is going to be a stream of ints, well then, yeah, we're going to generically strongly typecast it to be an int. All right, that makes sense. And then count is going to be our current place, which current will just go ahead and return. And then move next means we just increment count by 2 and make sure it's less than equal to 100. Now, those are both hard-baked because I wanted to make that similar to the comprehension from the Haskell example. And if we're still underneath that, great, we return true. Otherwise, we return false. There's nothing to dispose, so that just becomes a no-op. And resetting the iterator just sets the count back to 0, which means that if I got this code correct, I should be able to do that. And that would let me walk through each of the elements in that comprehension to, again, get us 2, 4, 6, 8, 10, 12, all the way up through 100. And now, again, there's a part of you that's saying, yeah, okay, but I don't generally need to, count numbers like that. And if I need to, we have the for loop, and I'm not sure that you're really saving me a whole lot. But bear with me here for a second. What if, again, now that we've liberated iterators from the idea of a collection, there are a number of things that they could iterate over. So, for example, we could actually think about the idea of the lines in a file as being its own collection. And normally this is a thing you've got to do with some for loops, and you've got to open up the stream and so forth. But if what I really want to do, because remember, the whole point of programming languages is to be able to very specifically and very directly express the intent of what I want to do. So in this particular case, I open a stream reader, and I will hand back the current line. I'll read the line when we do the move, and then I'll close the file when we dispose. And resetting, I just didn't want to bother because that's kind of past the point. The point here is that now, through this same for each construct, I can now loop through all the lines that we find in a file. And this is actually very specific. This is very deliberate in terms of what we are trying to work with. I am trying to go through the lines in the file program.cs, and for each line, there's my body where I just print out the line. Now, some of you who have explored this concept further, you may be waiting for me to mention the words yield return. Because, yeah, that's basically how we would do this. If you go look at the generated IL for the yield return statement, it would generate this exact state machine. As a matter of fact, the code will look very, very similar to this. And so you could say, I don't even need to make that an object, Ted. I could make file lines comprehension into a function, and we do all that same code, and we just yield return each time. And it's even fewer lines of code than what you had before. And you are all correct. You are absolutely correct. Yield return, this notion of a generator, this is the generator term is what we see from Python, by the way. And this idea was captured specifically in C# using the yield return compound statement. I'm not arguing with any of that. I wanted to go through the slightly more longer example because that's going to be a little bit more familiar to people who are using iterators from the Java world, as well as to people who just didn't understand what the hell yield return was supposed to be. So, forgive me for not bringing that particular bit of C# syntax to the front. And to be very clear, if you've spent time inside of C# and you've spent time talking about LINQ and so forth, if you've spent any amount of time in F#, yeah, you're probably already familiar with these things. So, booyah for you. But go back to that notion of infinite stream for a second, because both the numbers 2 through 100 and the file, those are both bound sets. Where exactly do we see an infinite stream? And if you stop and think about the world, there really isn't an infinite stream of anything except maybe time. I mean, time is supposedly finite, right? At some point, time will run out, and time had a beginning. But for all practical purposes, time is infinite. Is there anything that we deal with in terms of time? Well, yeah, we do get timer events. And if you start to think about it, this notion of just recurring elements that just keep coming. I mean, every time I move the mouse, every time keyboard input, those are all infinite streams. They're infinite streams of events. They don't all happen at the same time. But each case, we want to take one off the list, and we want to process that event And suddenly this whole new world starts to open up in front of you. And if you can grok just everything that I've just talked about, the idea that we respond to these infinite streams with a function, you have now essentially taken your first steps to understanding reactive and redux and functional reactive programming and all these other concepts that previous to this may have been closed to you. I am not going to stand here and say that this was easy. It took me a long time to wrap my head around the whole concept of Haskell and functional programming. But I'll tell you, as soon as I did, my code started to look very, very different. And it's going to take time. It's going to require an investment. And in many cases, particularly if you're me, it means wandering into places and wandering into technical spaces where if you're accustomed to being a senior engineer, if you're accustomed to being an architect and everybody giving you a certain amount of respect, when you wander into a new space, you won't have that anymore. You won't have that to fall back on. You go back to being the learner, not the master. And that is a valuable lesson that everybody really should carry away with them. I want to thank you for your time. I want to thank you particularly for your donations. And I, of course, want to thank my employer who was gracious and kind enough to sponsor this event. And now I will hand it back to the MCs.